Hello, this is Jonah Murovitz, and this is Physics 2211 Lab 5. Introduction. Purpose of this lab that I created was to observe 2D motion of an object and compare the ideal situation to a real situation. I set an object in motion with some initial velocity, observed the motion and calculated forces, and compared the ideal situation without forces to the real life situation with forces. Key concepts. So first we have force equals change in momentum over change in time. Not super important in this, actually. And then second we got position, final position equals initial position plus average velocity change in time. And then final velocity equals initial velocity plus F net over m, or acceleration delta t, change in time. Preview. In the ideal situation, the time it takes for the object to travel the distance is less than the real situation. This is because in the real situation, there are outside forces acting opposing the direction of motion, friction in this case, that slow the object's speed down by acting a negative acceleration on the object. System and surroundings. So the system is the object. Surroundings are table Earth. The Earth doesn't really matter here because it's not falling and it's resting on a table. Actually, it does matter when you have the normal force, but we'll get to that in a second. Initial conditions from tracker. So the initial velocity is around 4.494 meters per second. Initial position started at 0, 0. Real experiment. So this graph shows the x position versus time of the object, and as you can see, it's not constant velocity, and it's concave down. So that means there's an acceleration, and I am assuming that most of it is from friction for the sake of this experiment. And just from looking at the video, I was able to tell that the object, which is a pencil case, traveled 0 to 1 meter in 0.24 seconds and traveled 1 to 2 meters in 0.34 seconds. So it slowed down, even though it traveled the same amount of distance. Ideal model. So we have the initial velocity is 4.494 meters per second, as stated before. The initial position 0. Time to travel 1 meter and 2 meters should be the same as it is, because you have the t equals change in distance over velocity. Velocity is constant, change in distance is the same for both because it's just 1 meter. The differences lies in the time it takes for the object to travel 1 to 2 meters. In the ideal model versus the experimental model, the time to go from 0 to 1 meter was actually very similar, but the time takes to go from 1 to 2 meters is different because the effects of the frictional force will be more apparent over a longer period of time or distance. Calculating the force. So this is just a little extra step to see the coefficient of friction. So we first find the final velocity to be 2.353 meters per second from tracker, and using the acceleration formula, we have a equals delta v over delta t. Change in velocity is final minus initial over the change in time, just the time it takes to go the entirety of the run, so 2 meters. We calculated the acceleration to be negative 3.69 meters per second squared. Using that and the fact that F equals ma, you assume that the force of friction is pretty much the only force acting on it, and you calculate the force of friction to be negative 1.823 newtons. And since FF, force of friction, equals mu Fn, and Fn equals mg, which the mass of the object is 0.494 kilograms, we calculate mu to be negative 0.376, and since we usually take mu to be a magnitude, we just set it equal to the positive of that. Possible sources of error from this. Obviously, human error in tracker, air resistance not accounted for because we didn't account for that, and other energy transfers like thermal that I didn't account for. A discussion. What does it mean? This experiment shows how objects interact with each other in real life and the differences between an experimental model and an ideal model. It also exemplifies the limitations of using basic physics principles to predict motion, because there can sometimes be things unaccounted for, like friction or air resistance or thermal heat transfers. Conclusion. Using basic physics principles to predict motion of an object can be a very useful tool, but can also have some limitations. As shown through this experiment, when there are interactions that aren't accounted for, like friction, results calculated from an ideal situation can be slightly different from actual experimental results leading to some degree of inaccuracy.